professor in the Department of Statistics and Biomedical Data Science, and I am excited about this conference today, and I will be introducing the next speakers. So our next speaker is Judith Fan. She's assistant professor in the Department of Psychology, and she also has a courtesy appointment in education and computer science. She was also a postdoc here at Stanford before coming back as an assistant professor. She directs the Cognitive Tools Lab here at Stanford. The lab aims to reverse engineer the human cognitive toolkit, in particular how people use physical representations of thought to learn, communicate, and solve problems. Toward this end, it uses a combination of approaches from cognitive science, computational science, and artificial intelligence. Welcome.
Thanks, everybody. Is this live now? Are we live? OK, great. Yes, this is amazing. What a wonderful event. Thank you so much to the organizers for putting this together. It seems like a really, really exciting schedule. And I'm really honored and excited to be part of it and share with you some of the work that we've been doing harnessing data to various scientific ends. So in my research group, we study what we've been calling cognitive technologies. And by that, what I mean is like all the kinds of objects and devices and other kinds of tools that we use to support our thinking and communication with other people. We are interested in figuring out where these kinds of technologies come from, why they take the form they do, and how we can design them to work more effectively. So take, for example, something as simple and familiar as the number line. This is an example of a cognitive technology. It was a huge breakthrough when it came out, when it was invented, because as the Spanish architect Antoni Gaudí once observed, there are no straight lines or sharp corners in nature. But that didn't stop us from creating them anyway. And we didn't stop there. We extended the number line a few hundred years ago to create rectangular coordinates, which also turned out to be super useful. That technology converted all kinds of problems like these, where you might want to find the set of values that satisfies two equations, into the problem of locating points of intersection between two curves. And imagine what happened next to this breakthrough tool. It became something that we today could take for granted. And if all of those examples remind you of middle school and high school math class, let's just take a moment to marvel at that. Like, how did we get to this place today in the 21st century where an idea that was genuinely revolutionary a few hundred years ago is now elementary? So there are lots of ways of approaching that question, and I think that the tools of cognitive science and data science have a really big role to play here. So if you rewind back to 30,000 to 80,000 years ago, when anatomically modern humans began to mark up their physical environments, including these cave walls, they were essentially repurposing objects and surfaces in their immediate environment into carriers of meaning. So I know today is about modern data-driven discoveries, and I'm showing you cave art. I'll get back to that, I promise. What I want to show you all is that when you look at the story of human learning and discovery, the long arc of how we have come to understand the world's complex world that we live in, that story is incredibly intertwined with the story of technologies for making the invisible visible. So here are a few examples from the history of science, which I love. We have Darwin's finches in the top left here. And only when you see these individual specimens side by side does the importance of biological variation and where that variation might come from begin to pop out. We have the telescope resolving the orbit of the moons around Jupiter, which is the kind of resolution that Galileo needed to show the world that we might not be living at the center of it. We have Ramon y Cajal's drawings of the retina as seen under the microscope, showing us what different parts of the retina were and how they're hooked up to each other. We have Feynman diagrams in the 20th century, showing us how subatomic particles wink in and out of existence, events that we would literally not be able to directly observe with our own eyes. Now, among the most impactful of modern technologies for making the invisible visible, I'll argue, was the invention of the modern data visualization, familiar to many in this room, I imagine. So like the telescope and microscope, it helped the visualizations of data helped resolve parts of the world that we can't see directly with the naked eye. Unlike either of those optical technologies, data visualizations allow you to see patterns in phenomena that might be too large or too slow or too noisy to see directly. They're ubiquitous in the news, the cornerstone of evidence-based decision-making in business and government, and indispensable in every field of science and engineering. And so what I'm showing you on this slide is one of the first time series plots made ever. Okay? It was drawn by William Playfair in 1786 to show the balance of imports and exports from England over an 80-year period, from 1700 to 1780. And so for a while, as you can see, imports exceeded exports, but then the relationship flipped in the 1750s as exports really took off. But here's the thing. Unlike a drawing of one of Darwin's finches, if you hadn't seen one of these kinds of pictures before, it's not immediately obvious what you're looking at. But once you learn how, it's a kind of superpower. You can take an arbitrarily large number of observations and distill it into a single graphic that tells a story that you can read just by looking. And there are such powerful tools for helping people update their beliefs or those of others that developing the skills to read and interpret graphs has long been a core goal of STEM education. And it's only becoming more important over time. So the New York Times recently broke a story about recovery from COVID-related learning loss in mathematics. It's actually based on work led by folks right here at Stanford. And it looks like across a bunch of different states, the orange arrows are there, indicating that there's been some meaningful recovery, but there's still a long way to go. And we think that teaching core visualization literacy skills is a potent way of boosting quantitative and data literacy more broadly. So in our group, these challenges have inspired us to harness data to advance the science of how people learn to make sense of these kinds of graphics, so towards developing theories of how people learn to use these kinds of visualization tools to make sense of complex information and quantitative data, theories that will scale up to explain learning behavior in real-world educational settings. And so today, my plan over the next few minutes is to highlight 3 directions that we're pursuing in this vein. Our first question asks about the underlying computations or cognitive processes that are needed to understand what's going on in a plot. The strategy we're taking there is to obtain AI systems that can process questions about data visualizations, assess their alignment with humans, and then interrogate what makes the difference. Our second question uses data to ask what kinds of learning experiences help people acquire data and visualization literacy. So to get at that, we're exploring sources of individual variation across learners to understand what might explain those kinds of variation in college-level statistics and data science courses. And then we're also using data to ask what standards we should use to assess data visualization literacy. So to get at that question, we've been conducting a critical re-examination of existing measures of visualization literacy towards the development of improved and unified assessments. Okay, so going back to the top, if we were going to ask about the cognitive science of data visualization understanding, where should we start? Well, one basic ingredient is that we need some way of measuring understanding, of course. So here's what that might look like. Say you're confronted with this stacked bar plot, and someone asks you about the cost of peanuts in Las Vegas, okay, given this graphic. And they give you 4 options to choose from, okay? $12, $16.70, $23.40, or $35.40, all right? Think to yourself, what option do you think is most likely, okay? If you thought it was $12, you would be right, okay? But that's not what some prominent vision language models say given the very same question, okay? So, in a Herculean benchmarking effort led by Arnav Verma, an amazing researcher in my lab, we've been conducting careful comparisons between humans and AI systems on a variety of graph-based reasoning tasks, starting with these 6 tests that appear in this table. They include commonly used of graph understanding across the education, health, visualization, and machine learning communities. And all 6 of these tests were administered in as parallel a manner as possible to both human participants, as well as several state-of-the-art so-called multimodal AI systems that are capable of operating both over images and text inputs, and that had been claimed as displaying some competence, meaningful competence in a variety of other visual and maybe even quantitative reasoning tasks. And then we recorded not only the overall score achieved by people and those AI systems, but the full set of error patterns that they produced. And that allowed us to then assess, even when a model or a person gets a question wrong, to see if they were getting things wrong in similar ways. Okay? So here's what we found. I'm showing you for each of the 6 tests we included. They have funny names like GGR, VLAT, CalV, and so forth. And how well each of the models, okay, so those are the X-tick marks on this plot, in blue, orange, purple, and red, and how well they did to how well people did. And people will show up in green on this plot. So this is what we measured from the human participants. These are US-based adults who had taken at least one high school math class, and this is our benchmark here. This is where the models are across all those assessments. Okay, so it's a little hard to read, but we've got 2 variants of BLIP, 2 Flan T5, 3 variants of lava-based models, specialized systems such as Matcha and its base model Pix-Destruct, and also 1 proprietary system, GPT-4V. And across all 6 assessments, we see this reliable and meaningful gap between models and humans, a gap that we might have missed had we relied exclusively on chart understanding benchmarks that are currently most popular in the machine learning literature. And that's chart QA on the far right here, where the gap appears to be much smaller. We also analyzed the full error patterns generated by people and all these AI systems across tests. So this can be really revelatory when no one is quite at ceiling. After all, there's only one way to get all the questions right, but there are lots of ways that you can get things wrong. So we found that even though GPT-4V might look to be approaching human-level performance, none of these models, including our best performing systems, are making human-like error patterns. And so this is shown by all the dots on these plots falling well below the green shaded region, which represents the human noise ceiling here. So from that study, we made an attempt to understand the computations that underlie data visualization understanding, exploring the potential of current multimodal AI systems as a test bed for exploring hypotheses about the mental representations that could be supporting those abilities. But we've established that there remain barriers to developing computational theories that describe those cognitive operations, given that state-of-the-art systems still struggle with these tasks. Okay? So there are 2 ways forward. 1, to develop better models. 2nd is to probe the mechanisms in these models on simpler tasks. We're working on both now. Okay. The second question is about the kinds of learning experiences that help people acquire visualization literacy in real-world learning contexts. So to that end, we've been partnering with an educational research and technology development nonprofit based in Los Angeles. They're called Course Kata. And they've crafted a digital learning platform that delivers a modern data science curriculum and also an amazing resource for researchers who are seeking to use data collected on this platform to advance theories of learning about data science in this case. So we have been working with them to analyze, in this case, I'll be showing you results from a sliver of data collected in 2023 from 11 different institutions of higher education. So this is data aggregated from 45 different classrooms, and a little over 1,300 students are represented in this particular data set. what we are lucky to be in the position to do is analyzing longitudinal data that pertains to student mindset, engagement dynamics, and also learning outcomes for students in those real classrooms. So this gives you a sense of how the course is organized. There are interleaved surveys that act as pulse checks to ask students how they're feeling in their orientation towards material. There are these interactive learning activities in which we can measure real-time engagement, and also these interleaved formative assessments that are marked as these like quiz boxes on this slide, where we can actually probe ongoing learning. Okay, so what I'm showing you here is the distribution of engagement levels across students. In this case, how many of the interactive learning activities students completed in the material. Every curve on this plot is a chapter from that digital textbook from the 1st to the 9th. That's from darkest to lightest. What we notice here is how stable the shape of this distribution is over time within each course, and also how seemingly bimodal it was across students. We also found substantial variation across students with respect to how well they did on these pulse checks, checks of comprehension that appear at the end of each content chapter. So this distribution starts out tighter for early chapters, which are showing up in dark blue here, and then they kind of shift leftward and flatten as you move to the more advanced topics in this material. Okay, so we're in the process of continuing to dig into these data, so that's what I'm going to be showing you today from this project. But our goal is to map out how an individual student's engagement dynamics, how often, and how they engage with these open-ended learning activities that are embedded in the material relate to and predict what and how well they learn in these courses, okay, as expressed by their performance on these interleaved assessments. All right, so stay tuned for updates on that front. And then the third and final piece of this talk is one that poses a question about data visualization literacy itself and how we might go about measuring it. So in the first part, I showed you some results when we used these existing 6 tests of data visualization literacy. These are the ones that we have today. So our question in work that's now in press and led by an extraordinary postdoc in our lab, Eric Brockbank, we're asking, what are these tests actually measuring? Are they measuring these skills in the best way possible, or can we do better? So to get traction on that question, we started with these 2 on the left, GGR and VLAT, these being some of the most widely used and established tests in literature. And then we gave GGR and VLAT to a large and diverse sample of US adults. Some were recruited on a college campus, and others came from a demographically representative cross-section recruited via the prolific crowdsourcing platform. What I'm showing you on the left here is you get highly convergent estimates of the difficulty of individual items across both samples, whether the participant was recruited on a college campus or through prolific. On the right, I'm showing that people who did well on one test often also did pretty well on the other, suggesting that maybe these 2 tests are measuring similar things. So then what might those be? Perhaps the 2 tests track how much easier some kinds of plots are to understand than others. Maybe bar plots are inherently easier than stacked area charts or something like that. If so, then those plots should be reliably hard or easy across the board. But in exploring these data, we find that there's a lot more going on here. Performance wasn't always consistent, even for a given kind of plot, within or across these 2 tests. And then when we dug into the specific patterns of mistakes that people made, we found that the best way to predict those patterns wasn't necessarily the kind of plot, like, or the kind of question being asked, but other underlying factors. So here I'm showing you how much better a parsimonious 4 latent factor model does than one that uses the groupings that you might think we should use to organize the set of skills needed to understand data visualization. Okay. So to sum up, we found that there is some convergence between different ways of measuring data visualization literacy, but more detailed analyses revealed that it wasn't exactly clear what factors were responsible for that convergence. And given the limitations and the diversity and coverage of the kind of items in those existing tests, we actually need more comprehensive ones to identify what those factors are with more certainty. And all of this is ultimately in the service of using data to figure out how to help people think about data better. All right, so I want to recognize again all lab members, collaborators, and source support for the work presented here, and you all for listening. Thank you.
Hi, thank you for the amazing talk on such a wonderful topic. I have a question regarding your first point about like AI models are still kind of bad at recognizing graphics. I wonder, because I feel like the cause of peanut graph is kind of like a misleading graph on its own, like it's a very complicated graph. So I was wondering if this discrepancy between human performance versus AI performance is also true for the other like more I guess like clearer graphs. And also, do you see there's a use case for applying AI in terms of detecting like misleading graphic information? Because I think those are really common on the internet nowadays, and especially probably like pretty bad aside from the usability case, also like misleading for especially older folks.
Totally. Thank you. Thank you. Were you a reviewer on our paper? That sounds really familiar. Okay, so we actually included this third assessment that has the name CALVI for this very reason. So CALVI is a test designed within the visualization community that deliberately contains misleading plots. So these are ones with like y-axes that start at weird values, where like all kinds of things are like in orders that you wouldn't expect for ordinal data, all kinds of tricks like that. So you really need to like pay close attention to the labels to really draw the appropriate inferences, but they're adversarial. And so in some sense, like, is that what we mean when we're talking about data visualization literacy? I think reasonable people can disagree about the importance of overcoming those kind of misleading data visualizations. We include those, and you might notice here in that third panel, in the CALVI panel, the gap between all the dots that aren't green, okay, and the green dot is larger. So those are the harder items where both people are struggling, like the green dot is lower overall, and the gap is larger. When we looked at if there were other features, obvious ways of discriminating between, like if there was some way of like concisely identifying those factors that really tripped GPT-4V up, and like it was somehow stack bar plots or it, we didn't really find that. The gap is really broad spectrum. So across lots of different types of graph and lots of different kinds of tasks, we see this large and reliable gap. So it's not something that is as simple as that, but we're continuing to explore that. Thank you for the question.
Yeah, I loved your talk, and I had a question about, so you mentioned like the number line was this like innovation that wasn't common knowledge, and I'm wondering if you have any specific visions for how you can create a new normal through your work. New
normals. Whoa. Wait, sorry, could you unpack that? You say new, sorry, what did you mean by that?
Yeah, so did you have any like specific visions for like what do you see, how do you see this transforming like maybe education, for instance, and how people are learning this stuff?
Yeah. Okay, so the reason why we care so much about data visualization literacy is ultimately about people, right? Because like this is the case that I've been trying to make is like, this is our window into a complicated world, to take it down to size. Like, it's very, very difficult to see how the economy is doing just by opening your eyes, no matter how close you look, right? It really only comes in the form, like we first need to go and collect the data, wrangle it, and then put it in a form that is human interpretable, right? And that's really hard. And I think currently, the way in which statistics and data literacy are blended into the K-12 curriculum is not where it could be to set people up to reason about data, finite samples and uncertainty in a way that would really equip folks to really contend with how uncertain and complex the world really is. And I think that these tools, assessments, and also curriculum development is really in the service of really trying to make deeper investments in how we teach these core skills. Yeah, thank you for the question.
Thanks, Judith, again.